So my name is Esha Shah, and I'm here with my colleague Gentile, and we are part of the technical product marketing team at Mathworks for signal processing products. And today we'll go over some of the key concepts that can, in signal processing and the tools in MATLAB that can help you as you work on your solution for the SP Cup competition. So we'll take a look at spectral analysis, why it is important, and how you can implement it in MATLAB. Then we will take a look at phased array design, beamforming, and other important concepts for wireless communications. And then we will also cover the use of AI for signal processing. I do want to say, of course, that because it's a 1 hour webinar, we cannot dive into all of these topics in a lot of depth, but the aim is to try and point you to the right resources so that you can look at these topics as you go ahead. I also want to mention that we have a dedicated page for the Signal Processing Cup on mathworks.com. You can take a look at this page if you want access to the toolbox that we are going to be showing in the presentation today. And the page also provides other links to other videos, examples, resources that might prove helpful to you. So let's start with spectral analysis, right? So what exactly is spectral analysis? Spectral analysis is studying signals in the frequency domain. So while the time domain shows how a signal changes over time, the frequency domain analysis shows how the signal energy is distributed over a range of frequencies. And understanding the frequency dependency can yield a lot of meaningful information. And there are a lot of applications that use spectral analysis as a tool, of which RF and wireless communication is one. So to convert a time domain signal into a frequency domain signal, we can use the FFT function in MATLAB. And FFT stands for the fast Fourier transform, which is a fast algorithm that computes the discrete Fourier transform. And the output of the FFT is the magnitude response and the phase response. The magnitude response tells us the strength of the frequency components, and the phase response tells us how these frequency components align in time. Now, FFT-based techniques like periodogram or Welch's method are also used to calculate the power of the frequency components in the signals. So power spectrum and power spectral density are calculated using these techniques. And these are both of these are real and don't contain the phase information of the signal. So MATLAB has all of these different functions like p-Welch, periodogram, plom that you can use to calculate the power. For example, you can use p-Welch if you don't have enough information about the spectral content of the signal, whereas plom can be used to calculate PSD of non-uniformly sampled signals. In addition to these functions, to make spectral analysis easy for those who are just starting out and who don't know what parameters to select, what type of what method to select, we have the p-spectrum function, which is an easy way to get started. So you can just use it with you can just provide the signal and get the power spectrum of your signal, and this makes it easy to get started. And of course, the other functions will allow you to change the parameters and get a better result for your signals. So I'm going to show how we can do this analysis in MATLAB. So I'm going to move on to an example, and I'm going to show this in the Signal Analyzer app. So here we have a synthetic signal that I've created, and I think, yeah, and this signal has a 200 hertz frequency component, a 60 hertz component. I've also added in some low frequency noise or a trend, and then there is Gaussian noise as well. So I'm going to generate the signal and take a look at it in the time domain. And this is what the signal looks like. So now that we have the signal, we'll use the Signal Analyzer app to do the spectral analysis. The Signal Analyzer app is helpful because you can visually compare signals in the time frequency, and the frequency domains. So it's more about using the existing options, as we will see. So the app is open. I'm bringing in the signal and adding the time information in. Once not right now, I'm seeing the signal in the time domain, but then I can select the spectrum and take a look at the signal. Now here you can see that the 60 hertz component and 200 hertz component aren't really visible in the power spectrum. So there are a couple of things that we can do to resolve this. So we can go to the spectrum tab, and one of the parameters that you can control through the slider is spectral leakage. So there is a well-known trade-off between spectral leakage and frequency resolution. So the higher the leakage, the more frequency resolution you get. So I'm moving this along the slider, and when it's at the maximum leakage, I'm able to get good frequency resolution, and I'm able to actually see the components at 60 hertz and 200 hertz. Now, another thing that you can do in the signal analyzer is you can use the panner option, and this allows you to window through the signal manually. So as you slide through the signal, you can see the spectrum of that particular part of the signal. So when you move to the 60 hertz, you can see that component. And then as you move down, you can see the 200 hertz component showing up in the spectrum as well. Now, another technique that can be used for spectral analysis is using a persistent spectrum. So a persistent spectrum is basically a histogram of um, uh, of the frequency content, and you can see over here the 60 hertz the 60 hertz frequency persists in the signal, so we are able to see it, as well as the 200 hertz. So it shows the percentage of time that a given frequency is present in the signal. And the longer the frequency persists in the signal, the clearer it is in the display. And then finally, you also have the option of viewing the signal in the time frequency space. So here it gives you the information of how the frequency changes along with the time. So here we can see exactly where the 60 hertz component occurs and where the 200 hertz component occurs as well. So these are all tools that you can use to analyze all types of signals, including communication and RF signals. So this is basically how you can use the signal analyzer. It's a great tool to get started. Um, we have another tool called the spectrum analyzer, and this can be really useful for analysis of streaming data. So it with the spectrum analyzer, you can basically visualize, measure, analyze the frequency domain characteristics of streaming signals, like you would do in a hardware spectrum analyzer. And you see a lot of the same options in this tool as well. And you can use this for communication signals. So in a communication system, you can use the transmitted signal and the received signal and analyze them using the spectrum analyzer. And this can give you information about the noise that's being added in the channel, and it can give you a better idea of the communication system as a whole. So again, I'm going to show a quick example over here. And I have a simple Simulink model over here. And this okay, this model has the QPSK source, and then it had the amplifier, which I've gone into. The amplifier is adding in is adding in some distortion, and we are going to see the output of the QPSK source directly, as well as the amplifier. And I'm going to just run the model, and I'm able to see the spectrum analyzer here. I'm just going to pause it and show the features that can be seen. So one of the things that you can measure for channels is the ACPR, the adjacent channel power ratio. And this characterizes spectral regrowth in communication systems. So if there are components such as the amplifier, they may add in nonlinear distortion, and this is a great way to see the impact of that. So we can see that um, the um, ACPR for the QPSK source directly is lower than that of the uh, of the signal coming out of the amplifier, and uh, that is good to know. You realize that the amplifier is adding in noise into the source signal. Now, another thing that you can also measure is the occupied bandwidth for signals. So you can measure uh, uh, you can basically measure the extent of frequencies at which the signal energy spreads in a particular bandwidth, and it can be used to maintain standards of communication quality, and to diagnose if the communication system is degrading. The spectrum analyzer can be used for other measurements as well, like harmonic distortion, intermodulation distortion, to find peaks, etc. Now, the last tool that I want to talk about is the wireless waveform generator. Now, this is an app that's available in the communication toolbox, and it's really useful for studying various waveform configurations. So you can generate different types of waveforms like OFDM, QAM, etc. And in addition to being able to generate these different waveforms, what you can also do is you can add impairments and visualize the signal at that point. So when you generate the signal, you can see the spectrum analyzer, the constellation diagram uh, inside the app itself, and this is useful for studying signals and the effect of different RF impairments. So here you can add in noise like the Gaussian noise. You can add phase shift or DC offset. All of these different impairments can be added in, and you can see the output of those. So this brings us to the end of the spectral analysis piece, but I do want to say that there are a lot of examples in our wireless communication toolboxes that provide, channel estimation techniques, spectral masking, and other such features that are useful for studying communication waveforms. So with that, I'll hand it over to Rick, and he'll go into the next part of our agenda, which is the phased array and communications piece.
Great, thank you, Esha. Great information, and thank you, Professor, for hosting our session here. So welcome, everyone. As Esha said, we're really excited to show you these things. It's a great competition this year, the topic. So I want to change subjects here and go into the phased array and communications. And really, this is about looking at it at the system level. If you've seen the video that Professor Bornson did, you saw that it was in a scene, whether it was in a building or in a room, and being able to put an array in place and create beamforming and try to do these things. This is really what this section is focused on. So we'll start with designing phased arrays and generating array patterns. Then we'll talk a little bit about beamforming, and we'll talk about how the signals will propagate and how you can model the propagation paths through channel models, and also using ray tracing in the scene. Okay, so in this piece, we'll really start with array design. We'll move to, yeah,
Rick,
can you see?
No, I don't think.
Oh, you don't see the scene, I'm sorry. Oh, shoot, okay, sorry. Is this?
Yeah.
Okay, got it, sorry about that, okay. Thank you. So I was just on this one slide. So, all right. So we'll start with array design, move to beamforming, talk about channel models, and go into ray tracing. So that's the picture that we'll look at. And as Esha said, there's a lot of material here to talk about. So we're really trying to just make you aware of the kinds of things you can do, and then give you the links to the resources and help you with that. So we'll start with array design. And in MATLAB, you can design phased array systems. You can synthesize them. This might come in handy depending on how you're approaching the contest. You can build up arrays from subarrays. And this is very common in communication systems where you have large arrays and you want to be able to make them out of smaller arrays. It's a technique that's commonly used to save hardware by sharing transmit-receive modules in communication systems. We have workflows to model imperfections in the system, and this can be used in multiple ways. And possibly it can be adapted into looking at how some of the panels that you look at are modeled. And if you have data from solver-based systems or data that you've collected in the field, you can bring those directly into the model and increase the fidelity of the array design. So that's at a high level. Those are the kinds of things you do. I'll show you how you can do them now. When we think of an array, there's a lot of different parameters that go into array design, and it starts with basically where the elements are in space, and that really involves three dimensions: the X, Y, Z location, as well as a normal where the element's pointing. In this case, you see a rectangular array over on the left. We can apply a taper. Taper can actually be used to reduce side lobes in the pattern, but you can also make custom patterns. And that really goes into the next section, which will be in the beamforming of how you apply weights at the different elements to create a beam that you're looking for to either strengthen the signal or to focus it in a certain direction. And as I mentioned, it's very common, especially in large arrays, to be able to take subarrays and put them together into a larger system and build up a larger architecture. In this example on the right, you can see we've got a 3x3 set of smaller rectangular arrays that are put together to form a larger array. There's different design parameters that you have access to. For a linear array, it's the element type, the number of elements, how far are they apart, which axis are they pointing, what direction, and any taper that you apply. Very similar for a rectangular array, but just multiple dimensions. And then if you have something that's more conformal to a structure, you can build an arbitrary geometry array that conforms to a wall or to any kind of curved structure that you might see on the pole, for example. So that's very straightforward to put together in MATLAB. And as I mentioned, I just included this perturbed elements because you have the ability to control phase, amplitude, and position directly. So you can start to vary some of the parameters that go into the array design as well. So how do you get started on this area? We have a set of apps that I'll show you to walk through this. I included this just for reference. This is actually a 5G array panel that comes from this ETSI technical report that talks about subarrays and the ability to, or what makes up a subarray and how these subarrays are used to make a larger array. And this is an example of something you can take from a spec and take that same basic architecture, take the building block elements to use and feed them back up into the design. So here I've got a cross-polarization antenna element, one for each polarization. We put them together into one of those subpanels. And that means everywhere where there's an element, a cross-polarization element, I can put that into each one of these element locations. When I put them together and make a pattern out of it, I can visualize the pattern and steer that beam around depending on how I apply the weights. And then I can make a larger array. I take those subpanels, put them together and construct a larger subarray. So the point here is that if you have an architecture in mind or something that you want to start with, it's possible to, with just a few steps, to be able to build up and recreate that type of design. Now, the key thing, just like Esha showed on the signal analyzer, there's a corresponding set of apps that you can use to get started to design your array. And we have the sensor array analyzer, the antenna designer, and the antenna array designer. And these all have a home and a purpose in the workflow. And the two on the right are solver-based, which means that they use electromagnetic techniques and solvers to actually generate the patterns. The trade-off is you get a potentially more accurate answer, but at the expense of the time it takes to simulate. Now, if you design an element with these apps, you can bring them back into this one on the left rather, the sensor array analyzer, and use that to build up a pattern, a larger array pattern that uses the more accurate antenna element patterns that you build. Well, let's take a look at how that works in the system. So we're looking at phased array design and analysis, and some of those parameters I talked about, you'll see over here on the left, the number of elements, the spacing between the elements, any taper that you apply. And these are all areas that you can design and interact with on the left. In the middle and on the right here, you see that you can visualize all aspects of the array design. And you can actually see the array characteristics, things like the half power beam width, different side lobe levels, right? The key parameters that define that pattern. And just like the one Esha showed, you can generate MATLAB script when you're done. So whatever design you do in the app, you can click on this export button and generate the MATLAB script to then recreate it in MATLAB to further evolve it in your analysis. Okay, and there's a lot of different things you can do here: design the arrays, design custom antenna arrays, import antenna patterns, and generate the beam steering directly in the app. The other apps all have a similar look and feel. This is the antenna designer app. We start off by creating a new design. Here we pick the element. We have a long library of elements you can pick from. And once you select this, you simply give it the information that you're looking for. Here I'm kind of skinning down the list. We'll pick a patch microstrip antenna. We give it the antenna frequency that we want the antenna to resonate at. And when we say go, it gives us the design. We can look at things like the impedance, the S parameters, the current on the element, 3D pattern, azimuth, elevation, all the aspects of the antenna element. And then once you're done with that antenna element, you can take that and put that back into your array design and build up a larger pattern for it. Okay, so that's going to be one of the pieces we have here. There's a very similar one that you can do the array design at the solver-based level for higher fidelity. So this is just to make you aware of these apps that exist, how they connect together, and how they can be used to generate that front-end array design in your system. Once you have the array in place, the beauty of the array is that you can apply weights to the different aspects of the elements. And with that, you can create beams. Why do we create beams? We may want to focus the energy in a certain direction. We may want to use beams to create nulls in different directions to eliminate interference. For example, if I have an interference source, I might be able to form a beam where I have my null in the direction of the interference source. A lot of applications here. In this kind of competition, you'll be generating a beam from the initial antenna, and you may be able to figure out what the beam needs to look like coming off of the reflected panel. So the basic framework, building on what Esha showed you earlier, the waveform generator is there. Anything that you can do in the waveform generator, you can also write code for in MATLAB. Just like the apps that I showed you and that Esha showed you, you can click a button and generate the MATLAB script that goes with it to program in MATLAB. We take the output, those waveforms that we generate, those distorted waveforms or whatever library of waveforms that you pull out of the app, send them through propagation channels, and then we can, when we're doing the receiving or transmitting, we have the option of doing beamforming. We could form a beam on transmit, or we could form a beam on receive, or some combination. And the idea here is that the beamforming algorithms have to understand what the array design is. So all the array design pieces I showed you in this first little section get captured into a container. And that container is digested by the beamforming algorithms. So it knows how many elements there are and how to steer the beam in those directions, either in azimuth or elevation or some combination. Okay. Along with that, that's where we get the weights and the steering from, right? We apply weights to these antenna elements, and we can form a beam. There's a lot of resources to get started here. We have lots of different beamforming examples. The beamforming could be useful in ways of generating the initial signal coming off the antenna, but it also can help you understand what the beam needs to look like off the reflective surface, back to whatever system that you're going to be looking at. So we put a link here to some examples to get started with on beamforming. The documentation also includes many functions that might be useful to generate the steering vectors for these types of beams. So if you know you want a beam to look like a certain in a certain angle off of a certain array type, you can generate the coefficients that would generate that beam. what do the coefficients mean? The coefficients are the values, the complex values that are applied to each element or to each panel or however you're forming a beam to figure out what they need to be. When they're applied, they create the corresponding set of delays in the signals that go out the elements. And when they combine in the far field, they have an ability to focus the energy in a certain direction. So you see here, in this case, there's beamformer weights, other valuable ones, the steering vector. This creates a steering vector that you can use to basically generate the weights to point a beam in a certain direction. And there's also algorithms here to generate multiple beams based on the channel that the signals are going through. That brings us to channel models. So we have a lot of channel models to pick from. Our line of sight, LOS is line of sight. That's from sort of point A to point B, transmitter to receiver, for example. These include things like the effects of weather, rain, gas, and fog, for example. Some of the communications frequencies are impacted by oxygen levels in the air or atmospheric conditions in the air, things like this. Various communication specific channels, including ray tracing and what we call our scattering MIMO channel. Scattering MIMO is important because it allows you to digest the array that you've designed. The array pattern contemplates that. It also allows you to put scatterers in the path of the transmitter to receiver. So you have a propagation path, you can put scatterers there and get the reflections off of those scatterers in the field of view of the signal that it's propagating. Now, I include the documentation here as a useful link as well. These are some of the path loss calculations based on the atmospheric effects. We also have some of the line of sight calculations where you can calculate the signal strength from point A to point B. And notice also the option to do ray tracing, right? So that brings us to the next section, which is in ray tracing. So how do we set up a scenario that you can use to test your algorithms and recreate that kind of a scene? So this is a picture in an urban environment. We've got a transmitter in the park. We can see line of sight. The green represents where the signal can travel, and the red is where it's occluded by the structure. In this case, green to green between the red and blue lines or pins means that we have line of sight connectivity. What's nice about these kinds of things is you can click on the links here, and this propagation path information comes up, tells you the distance. It tells you the angle of departure, angle of arrival, as well as any phase change or path loss of that path. And you can see the different paths that it takes. You can specify the number of rays that you want to capture in this kind of a scene. For indoor scenes, you can take in an STL file, which describes the inside of the building. In this case, you see a room. There's a small red dot here, which is the transmitter, and the blue is the receiver. We can see from the red to the blue what are the paths that we take. And it's just, most of these things are just a few lines of code to propagate the data, propagate the signals using, in this case, ray tracing, what the coordinate system is, number of reflections, and the material that it's reflecting off of. And you can build up this kind of a picture with ray tracing in a nice way to figure out sort of without any enhancing, what does the signal look like there? And as you start to evolve in competition, you can figure out good versus bad. Is something good now, or is it better in another way? I think this is a nice plot because it also shows you the different magnitudes and the delayed signals and how they may interact in the system. And that's important as you start to figure out how to improve the signal at the receiver. For outdoor scenes, we can generate a scenario. This is based on a system called OpenStreetMaps. So for this kind of a scenario, this is actually Canary Wharf in London. We can go to OpenStreetMaps, give it the coordinate system, download an OSM file, OpenStreetMap file, import that into the tools, and be able to start with a scenario. We can mount a transmitter and a receiver in the neighborhood in a dense urban environment. You can see the rays going from transmit to receive in the picture. We can look at broad coverage and paint the coverage on the map, and you can see what the signal strength is as it sort of disseminates from the transmitter. You can also determine individual path coverage. So if I was driving or walking in a scene, I could see, let's say I was worried about a dead zone. I could see my signal strength as I take a trajectory through the urban environment. You see that reflected in these little dots here. That was my path, and I'm taking samplings of different signals that I'm looking at, signal levels. But connecting the dots with what I talked about at the beginning, we can build up an array. Put the array here instead of an omnidirectional pattern. This is more omnidirectional in this broad coverage area. But what if I want to focus it? What if I want to use the array to focus the energy? I can then take that array design, put it into the scene, and have additional focused energy that's going to be coming out of the transmitter in this neighborhood, and evaluate what kind of a difference that makes as I'm steering the beam around. Extending that for one more piece here, you see the different types of channel models. You can see that these colors represent the different strength levels. Of course, if you click on them, you can see the value itself, and you can get that in MATLAB directly. You can see that in addition to the direct paths, you're also able to get reflections off of the material. You can specify what type of material it's being reflected off of. And you have the ability to add an array design at the front of the transmitter and at the receiver. Okay. So again, it's just wanted to give you kind of a broad brush overview of the system level kinds of things you can do to build on some of the more detailed signal processing things that Esha showed you to start. Put these together. The tools that are used here are phased array for that large phased array design, the antenna portion, and then the communications toolbox. Those are all part of the package you have access to. Okay. All right, Esha, I don't know if I'll stop sharing here. Do you want to go to the next section?
I can share my screen.
Okay.
Is my screen visible?
Yes.
Okay. So the final piece that we wanted to go over was, talking about the AI workflow, the tools that, again, you can use in MATLAB to either get started, or if you are an advanced, if you're an advanced user of AI, then you can, then how you can use these tools in that case. And I'm going to go through the AI workflow and then point out a couple of areas where we've applied AI for communication and wireless signals. So, talking about the AI workflow, most commonly the machine learning and deep learning workflows have these three steps. The first is data preparation, which includes data labeling, cleaning the data, basically getting it ready to use for training and testing the model. Then the next step is actually building the AI model, and this can be either machine learning or deep learning, and you can then train it on the data that you've either generated or collected, and then test the model as well. And then the final step typically is deployment into the field. I'll go through how the tools, I'll point out the tools in MATLAB that you can use for each of these steps. So for the data preparation step, sometimes data collection is not possible, or in case of wireless, you may just want to synthetically generate your data to begin with, and in that case you can use different things in MATLAB. So you can either simulate your data using models and deep learning. You can generate wireless waveforms like we saw, add RF impairments, channel effects, etc. You can, if you're working with radar signals, you can generate that data as well. And then if you're working with specific data like audio data, then you can augment it or generate it using functions like text to speech. And this allows you to have sufficient data to work with. So even in the cases that you already have data, you may augment it with some of these techniques. And again, there are apps to make it easy for you to get started with the process of labeling and pre-processing. These are time-consuming steps in the workflow. So we have the signal labeler app. You can bring in whatever signal you're working with, and if it's collected data, then it's likely unlabeled data, and then you can use the app to label it. And again, the Signal Analyzer app is a great app to not only do spectral analysis and time frequency analysis like we saw, but also to try out and iterate on what might be the best pre-processing technique to use for your data. Then you can um, extract different kind of features from the data. So I'm sorry. Your uh, f- da- the features that you collect can be either time domain features like signal patterns, peaks, etc. Frequency domain features like bandwidth measurements, spectral statistics, etc. Time frequency maps that are generated using short time Fourier transform or the continuous wavelet transform also are excellent features to feed into AI models for training. And then there are a lot of different algorithms that will generate more domain specific features as well. And the the reason that feature extraction is important is because it reduces the variability and dimensionality of the data, and it makes um, it makes it so that the AI model then learns the relevant features. Um, it, it's basically reducing the noise in the data that you're feeding in, and uh, then coming to the next step of AI model building, um, you you again have apps. The Deep Network Design is a great app if you're looking to either build a model from scratch. Then you can use the drag and drop functionality here and quickly get started building your network. There are a lot of pre-trained models that are available as well, and you can continue on to training the model from within the app as well. Um, there are equivalent apps for machine learning workflows as well, like the classification learner or the regression learner, and then more workflow oriented apps like the experiment manager, which can help you when you need to iterate to find what model might work best for your application. And then finally, coming to the deployment piece. Now, this might not be relevant to you in this particular competition, but you can generate code for deployment to a lot of different platforms using the code generation capabilities in MATLAB. Um, but let you know, so this basically sort of sums up the the value that Mathworks adds to each step of the workflow and how it makes it easier. Um, but what I want to talk about is this particular example. We have this example which does automatic modulation identification of communication waveforms, and this example again is available in the documentation. So in RF applications like intelligent receivers, radar interference detection, or spectrum management, automatic modulation classification is really useful. So when the receiver receives the signal, it uses a trained neural network to classify from eight possible classes. So um, yeah, so over here you can see the received signal is then being classified, and you're able also to see the probability of it being in one of these classes. So this is really useful to also understand um, the, how your model is doing the classification. Um, and the way this example is set up, we generate data using the tools we've spoken about earlier. So we generate all of the waveforms synthetically. Then we use the continuous wavelet transform to extract the features. In terms of building a deep network, because this example is targeted to people who might not have a lot of deep learning experience, it actually uses transfer learning. So you're just using a pre-trained model and then repurposing it for this particular application. And again, this example goes all the way to deployment. If that's something that that you're working on, then that's something to look at as well. And finally, I want to talk about reinforcement learning and how that might be helpful for complex signal processing problems. So reinforcement learning is a type of machine learning in which the computer learns to perform a task through trial and error interactions with a changing environment. And this learning approach is basically, it enables the computer to make a series of decisions that will maximize the reward metric, and there is no explicit programming done to achieve this to achieve the task. So if you consider the case of self-driving cars, with reinforcement learning, you don't have data points at the beginning, uh, and the data is being generated as the agent or the computer interacts with the surrounding, and then the required behavior is learned. So then the car will learn to drive without colliding into other vehicles. So let me go into a little more detail about this piece and explain what I mean by agent and what actually is involved in a reinforcement learning workflow. Let's take again the self-driving car example. In this case, the agent is the either the vehicle or the vehicle's computer, and it that is basically what determines the action that's being taken. So the um, observations are basically is basically data from the different sensors that are attached to the car, and the environment is whatever the road conditions may be, the pedestrian information or any other such information is basically the environment that is always changing, as you can imagine, when you drive a car. And the action is uh, the different possible behaviors for that the car can take, right? It can either overtake a car in front of it, or it can just stay in its lane. It can do all of these different actions, and the way the car or the agent determines what action is to be taken is by policy. So um, and the way the policy works is there is a reward, and here the reward may be anything from you know uh, fuel efficiency or comfort of the driver, or any such thing that you want to basically optimize, you want to maximize that, and that then drives the reinforcement learning algorithm. So the algorithm is not uh, actually designing the controller itself, but the machine is designing its own controller over here, and then through these trial and error processes, um, and by using the reward as a guide, the agent learns the sort of the right output and the right action to take. So this is really useful, and uh, we have a user story of how reinforcement learning has been used for cognitive radar systems. So these are systems that are able to adapt based on environment conditions, and reinforcement learning in this particular application was used to optimally utilize the radar resources. And there's a video on our website, and that goes into a lot of detail about the way reinforcement learning is being used over here. Um, but that brings us to the end. One other thing that I do want to point out is, in addition to all of the resources that we've been mentioning, uh, we have on-ramp courses. So especially in areas like maybe AI, where you may not have experience, or you want something to get started, these are really great courses. They are free. They are about 2 hours in duration each, and they go through a lot of examples that you can actually implement and try out. So it can be a really good resource to get started. But that basically brings us to the end of of the presentation portion, and we'd be happy to answer any questions that you have now.